Hi, today we will look into the design of the C-clamp. Let us read the question. The maximum force exerted by a C-clamp is 100 kN. Height of the screw is 550 mm. Frame overhang is 450 mm. We need to design the following: screw, nut, body frames and handle. Let us look into the solution. The given data are as follows. Force exerted is given by capital P, that is 100 kN. Height of the screw is given by HT, that is 550 mm, and frame overhang EO is 450 mm. Some of the parts in the C-clamp as are follows. Screw is given by this diagram, nut, body frames and handle. So these are the parts in the C-clamp. There are two types of nuts, solid nut and split nut. Solid nut is a one-piece nut, whereas split nut consists of two halves and they are joined together by the help of set screws. Now you can see in this nut the flange part is at the bottom and at the top there is no flange. Similarly, you can see this type of nut where no flanges are there at the bottom as well as at the top. And in this particular screw you can see it is a square threaded screw and the nut is made of brass. And the nut is in two halves. The designer has the choice whether to select a solid nut or a split nut. In case of solid nut, cannot take care of the wear, whereas the split nut, the wear can be taken care of by tightening the set screws, and then the gap between the screw and the nut can be reduced. These are the different applications of C-clamp. Here, clamps hold objects firmly in place, whether it is being used to clamp an object to a work surface or to hold two or more objects together. The purpose of a clamp is to provide a strong grip between the two components or three components that are attached together. They can be used for different operations, like it can be used for polishing, it can be used for drilling, it can be used for leveling. However, if a clamp has two jaws, they will work together to hold the item. In this you can see that there are different assembly and sub-assembly of the C-clamp. This yellow part is called as the frame. The blue part is called as the handle. The handle is connected to a screw and the whole thing is called as a screw. The screw mates with the nut, which is shown in the green color, and the screw goes through and through and touches the flat part of the frame. You can observe the screw also has a flat part which touches the flat part of the frame. This is how it is connected. If you can see the flat part, it is called as the collar of the screw. This thread portion is called as the thread part of the screw, and the upper portion is called as the shank part of the screw. There is a screw head to which handle is connected. This is an assembly which shows the screw and the nut, and here is just a part of screw where nut is not present. This gives us a complete idea how they are assembled together. You can also observe that this is the frame and the frame has a slot. Within the slot the nut is added. The nut consists of a flange part and a cylindrical part. The flange of the nut restricts through and through motion of the nut from the frame. Hence the nut is fixed in that location due to the flange of the nut. Let us look in some of the nomenclatures in the C-clamp. Here you can see the frame has a section and that section is an I section. In this figure you can observe that the end of the nut and the end of the flat surface of the frame, the distance between them is called as a throat of the C-clamp. The height of the nut is given by HT. If you add the throat of the C-clamp plus HT divided by 2, what you get is L, which is known as the unsupported length of the screw. The edge of this frame and the center of the screw, the distance in between them is 450 mm, which is called as frame overhang. Now the length of the job has to fit in this particular place. Half the job will be in this space and the half the job to the right. Total length that can fit in this space is 900 mm. Now if you want to increase the length of the job, the frame distance or the frame overhang distance has to be increased. Let us start with design of screw. The material justification goes like this. The screw is under compression stress when the load is steady, but screw also undergoes torsional stress when the screw is rotated due to frictional movement. Screw is subjected to buckling load as well. Considering all these points, the screw is made of steel will withstand all the stresses. The material can be plain carbon steel. The grade of the plain carbon steel can be calculated and found out. Types of threads. There are basically two types of threads. square thread and isometric trapezoidal thread. These are the two threads which are very commonly used. There is acme thread, which is a special type of trapezoidal thread, and buttress thread, which is a combination of square thread and trapezoidal thread, but it acts only in one direction. So we'll compare between square thread and isometric trapezoidal thread. The advantage of square thread over trapezoidal thread are as follows. The efficiency of the square thread is more than the trapezoidal thread. There is no radial pressure or side thrust on the nut. Therefore, selecting square thread for our C clamp. There are two types of threads, that are right hand thread and left hand thread. Generally in C clamp, right hand thread are used. Therefore, selecting square thread with right hand screw. The square thread consists of three series: fine series, normal series and coarse series. The pitches and the range of the pitches vary with respect to the type of series, and the depth of thread engagement also varies. Considering moderate pitch and moderate depth of thread engagement, selecting square thread with right hand thread as well as with normal series. Unit pressure on the thread. Depending upon the material combination, the unit pressure on the thread changes. The unit pressure on the thread is given in PSG page number 7.87, which is represented by small p. Steel screw and bronze nut consist of 120 kgf per centimeter square. Steel screw and cast iron nut consist of 80 kgf per centimeter square. Therefore, for design to be compact, considering steel screw and cast iron nut with 80 kgf per centimeter square, which is equal to 8 Newton per mm square. The terms in the square thread are as follows. T2 is the depth of the thread engagement, as shown here. H is the thickness of the thread base, as shown here. D0 is the major diameter or nominal diameter. D1 is the core diameter. DP is the thread pitch diameter. P is the pitch. These terms are discussed in the PSG page number 7.87, and all the formulas that are connected with the square thread design is present in this particular page. So we discussed the terminology here. Lead is equal to Z into pitch, where Z is a number of starts. We assume that selecting single start for the thread we have selected, as production cost is reduced when we select Z is equal to 1. Therefore, S is equal to pitch, that is lead is equal to pitch when we select number of start as 1. Design of the screw. We find this formula in the page number 7.87, where psi is ratio of HT upon DP, where HT is the height of the nut. This ratio for solid nuts is between 1.2 to 2.5. For split nut, it is 2.5 to 3.5. We select here a solid nut, so the value of psi becomes 2. Capital P is the force exerted, that is 100 into 10 raised to 3 Newton. Small p is the unit pressure on the thread, that is 8 Newton per mm square. Putting values into this particular formula, we can find out the pitch thread diameter, which is 63.07 mm. DP, here it is 63.07 mm. We know DO plus D1 equal to 2 into DP. 2 into DP is 126.14 mm. In PSG 5.71, the values of major diameter, minor diameter and pitch is given. We can know that the major diameter and minor diameter, when they are added, we get the values like 120 mm. But we see that 120 mm is less than 126.14 mm. Similarly, when we add 68 and 58, we get 126 mm, which is again less than 126.14 mm. The next value is 70 and 60, and that is 130, and 130 is much more than 126.14. Since 130 is more and safe, we select major diameter to be 70 mm, minor diameter to be 60 mm and pitch to be 10 mm. All this data we have extracted from 5.71. Now we know DO is 70 mm and D1 is 60 mm. Hence, using this formula, we can find out DP, which is 65 mm. Here, while looking into this table, there is some difference in terminology with respect to dimensional values and formula. The dimensional values are given in 5.71 and the formulas are given in 7.87. The depth of the thread engagement is given as H1 in 5.71 and T2 as 7.87. Both of them are the same thing, but the terminologies are different. The value remains the same. Similarly, thickness of the thread base is given as E in 5.71, H in 7.87, but the value and the term remains the same. Hence, this particular point needs to be seen. To check if the screw is self-locking or overhauling, friction angle rho is somewhere from 6 degree to 8 degrees. Rho is 6 degree. Assume that helix angle beta is tan inverse of S divided by pi dp. When we put up the values, helix angle comes around 2.803 degrees. We can see that rho friction angle is greater than the helix angle beta. Hence, we can conclude the screw is self-locking. We can also calculate the value of mu. Mu is tan rho. When substituted, it comes around 0.1051 degrees. We know that lead, that is S, is equal to 10 mm and T2 is equal to 4.5 mm. The stresses induced in the screw are the following: direct compression stress, torsional shear stress and buckling. Direct compressive stress induced in the screw is given by this formula, and here the minor diameters is represented by D1, which comes around 35.37 Newton per mm square. The total torque induced in the screw is given by MTT. MTT is the combination of MT plus MF, where MF is torque induced to overcome the collar friction and MT is torque applied on the screw. This formula is given in 7.78. We can calculate MF. MF is equal to P into D red multiplied by mu upon 2. This is given in 7.87. We know D red is 1.2 D0 and it comes around 80 mm. This is an assumed empirical relation. By substituting other values, MF can be calculated as 441.42 into 10 raised to 3 Newton mm. Similarly, we can calculate torque applied on the screw, MT. It is given by this formula, which is there in 7.87. After putting the known values, the MT value comes around 1006.601 into 10 raised to 3 Newton mm. The torsional shear stress induced in the screw is given as MTT upon ZP, where ZP is pi by 16 D1 cube. Rest of the values we are aware, hence the torsional shear stress comes around 34.14 Newton per mm square. Once we have found out sigma and tau, we can find out combined stress sigma com. Sigma com is under root of sigma square plus 4 tau square. We can put the values and sigma com comes around 76.9019 Newton per mm square. Calculate factor of safety according to VM fares. Assume load repeated in one direction for the screw. The factor of safety according to VM fare comes around n is equal to 3. We know this formula sigma com is less than or equal to sigma y upon n, where sigma y is yield stress. We know sigma com and n, hence sigma y comes around 230.705 Newton per mm square. We can select a material based on this particular value of yield stress. After looking into PSG page number 1.9, C15 appears to be an apt value. We have selected C15 because the cost is low and it is easily available. The actual yield stress value for C15 is 240 Newton per mm square as given in PSG 1.9. The next point is to calculate the buckling load on the screw, which is given by PC. For end conditions N, we can consider screw to be a column. We understand that at the top portion there is a nut and at the bottom portion there is a job. So we can consider the top portion as hinge and the bottom portion as fix, and L is the distance of the whole screw. For such a combination, the end condition is 2 as given in PSG 6.8. This figure is also given in PSG 6.8. To calculate L, the unsupported length of the screw, we know the formula. So L comes around 615 mm. The least radius of gyration R is given by under root of I by A. We know what is I and we know what is A, hence R comes around 16.25 mm. The slenderness ratio L by R now can be calculated, which comes around 37.84. If the slenderness ratio is greater than 120, we can use the Eulerian formula. If L by R is less than 120, then Johnson's parabolic formula can be used. Since L by R is less than 120, we are going to use Johnson's parabolic formula. PC, Johnson's parabolic formula, is given in PSG 6.8. Here, A is the area, sigma y is the yield stress, N is the end condition, capital E is the Young's modulus. Hence, after substituting the known values, PC comes around 778.66 into 10 raised to 3 Newton. For buckling load PC, we can find out the factor of safety. The factor of safety is PC by P, where capital P is the applied load. After calculating this, the FOS comes around 7.786, which is much higher than the assumed factor of safety 3. Hence, we can say factor of safety is satisfactory in case of buckling load. Let us summarize the screw. Material is C15, total length is 680 mm, selecting square thread right-handed normal series. DO is 70 mm, D1 is 60 mm, pitch is equal to lead and that is equal to 10 mm. DP is 65 mm, H1 is 4.5 mm, E is 4.5 mm, bottom collar diameter D red is 1.2, D0 that is 80 mm. Design of the nut. The nut drawing is as shown in this figure. Figure is not there present in the PSG 5.69 very clearly, but the nomenclature is definitely there. Material is cast iron. It is low cost and easily available. GCI 15 is the grade of the cast iron, which is present at the page number 1.4. SUT is 150 Newton per mm square. Assume factor of safety as 3 mm. Design sigma T is 50 Newton per mm square. Design shear stress is 25 Newton per mm square. Design bearing stress is 8 Newton per mm square, and small p here is unit pressure on the thread. The value is obtained from PSG 7.87. Nut height HT is given as 130 mm. DO is 70 mm. D1 is 60 mm. Pitch is 10 mm. Number of threads on nut is given by N. N is HT upon P. P is a pitch. So there are 13 number of threads on the nut of the C clamp. The failure that takes place in the nut thread is shear failure in the nut thread and bearing failure in the nut thread. Let us look into it. The shear failure in the nut thread is given by tau is equal to P upon A. You can look here what is DO and E. When the failure of this nut takes place, you can see at the red lines are the places where the failure takes place. After the failure, the nut will look like this, where all the extended projections are abraded off due to the shear stress, and therefore the area here now becomes as pi DO E into N, where N is the number of threads. When we put up the known values, tau is 7.77 Newton per mm square, which is quite less than the design shear. Hence we can say that the design is safe in shear failure. Bearing failure at surface of contact between the nut and the screw thread. Now here is the figure, and the threads of the nut are in contact with the threads of the screw. In between them always the bearing stress takes place. The area here can be given as pi by 4 DO square minus D1 square into N. After substituting, we get value as 7.53, which is quite less than the design bearing stress. Hence we can say that the nut is safe in bearing stress as well. Let us start with the design of the body frame. The material for the body frame is grey cast iron, low cost and easily available. Sigma UT from PSG 1.4 is 150 Newton per mm square. Assume factor of safety to be 3, hence design sigma T is 50 Newton per mm square. Section of the frame. It can be I section or rectangular section. We are selecting I section for frame because it induces less bending stress than rectangular section with respect to same material consumption. Orientation of I section. It can be horizontal I section or vertical I section as seen in the figure. You can also see here more clearly. Here is the C clamp with the horizontal I section, and here is the C clamp with the vertical I section. Since the bending stresses induced in the horizontal I section are very less compared to the vertical I section, we would be considering horizontal I section for our design. Standard horizontal I section. There are two standard horizontal I section, 60 into 40, 90 into 60. For the initial trial, we will assume the smaller one and take that in consideration. So selecting 60 into 40 section. After that calculation, if 60 into 40 fails, we can take 90 into 60 into consideration for the design. Assuming B upon A is 1.5. This particular distance of I section is called as B, which is 60, and A is equal to 40. So when you divide B by A, you're supposed to get 1.5T. That's an assumption. Selecting 60 into 40 section, we are very much interested to calculate the area of the cross section. To calculate the area of the cross section, assume 1, 2, 3, 4 at the points to be a rectangle. In this rectangle, we will subtract smaller rectangles, that is 5, 6, 7, 8 2 times. Hence we will get the area of the cross section. So the area of cross section comes around 12T square, where web T here and web here both have T as the dimension. Bending of the frame takes place at centroid YY axis in the cross section. Given section is I section 1, 2, 3, 4. In this case, bending is vertical axis. Hence, neutral axis of the cross section is vertical. Therefore, neutral axis cuts the dimension 60. Therefore, y is equal to 60 by 2, that is 3t. So, we have calculated the y for I section. Once y is calculated, we are interested to find out the moment of inertia at YY section. So, this is one rectangle and this is the smaller rectangle which we generally subtract. According to IYY, in this particular rectangle section, we can say that since it is cutting 60, the YY is cutting 60, so 60 cube into 4t upon 12 minus 2 times, because there are two sections like this, it is cut at 40 cube into 1.5t upon 12. When you try to calculate it, it comes around 56t raised to 4. ZYY can be calculated like this, IYY upon y. So when you try to place the knowns, it comes around 18.67 t cube. Let us try to find out direct tensile stress in the frame. The direct tensile stress is P upon A. We know P, we know A. It comes around 8.33 into 10 raised to 3 upon T square. Bending stress in the frame can be found out by this formula, PE upon ZY. PE, where E stands for eccentricity. We know that the frame overhang distance is 450 mm and the total width of this particular I section is 60. The neutral axis is 3t. So the eccentricity is 3t. Therefore, P into E upon ZYY. When you try to put up these values, you can get an equation for sigma B. Now we try to find out resultant stress and size of the I section. Resultant stress, that is sigma T max, is given as sigma T plus sigma B. It should be less than design sigma T. Design sigma T we have already calculated. Putting up the values of sigma T and sigma B and then solving the equations, we get it in the degree of T raised to 3. We can solve this equation and we can calculate T to be 40.84, which can be approximated to 41 mm, and A is 40, so it becomes 164 mm, B is 60, so it becomes 246 mm. So the frame size is 41 into 164 into 246. The next is the design of the handle. The handle is made of C30 as the material. It is low cost and easily available, hence we are selecting that material. Sigma SYT is 600 Newton per mm square from the PSG page number 1.9. In this figure, you can observe that LH is the length of the handle and DH is the diameter of the handle. You can find out sigma T. You can calculate sigma T to be 100 Newton per mm square. The total torque to raise the load can be given by this equation, MP is equal to P into LH, where P is the applied load, L is the length of the handle, M is the moment. Now we know that MB is equal to MTT, which we have earlier calculated. Therefore the equation becomes like this, LH into P into MTT. Now the force that you are going to apply, that can be calculated using ergonomic consideration. Let us understand and assume that there is a single operator and this is an intermittent use. So for intermittent use, the force is 400 Newton. Hence the P value where the operator will apply force would be 400 Newton. Let us put up in this value, LH is equal to MTT upon P. So MTT we already know, P is 400, the operator force. The length comes around 3620.05 mm. Note that the length of the handle is too large and impractical. Introducing a rolling friction will solve the problem. Introduce a single thrust ball bearing. Therefore, neglect collar friction torque and the length of the handle can be recalculated while redesigning. At this point of time, we are not redesigning it. Design of the handle. Let the handle be through and through type. The handle is subjected to bending stress. Sigma B is MB upon pi by 32 DH cube. Substituting here the values, we can find out DH. DH turns out to be as 52.83 mm. At this point of time, we can stop the design of C-clamp.